Hey there, how are you? Today we're going to finish up, chapter 10, and we're going to talk about, briefly, we're going to talk about functions. So, what is a function? A function is a set of ordered pairs. A set of ordered pairs. So, let's write that down, set of ordered pairs. And what are ordered pairs? Points, right? X is X and Y. Pairs of X and Y coordinates. So a function is a set of ordered pairs that assigns a unique value, a unique Y value to every X value. Meaning what? Meaning an X value of 1 can only be paired up with a single Y value. So 2. Okay? Now we can determine if a set of ordered pairs is a function either by looking at a set of ordered pairs written out or by looking at a graph. Okay? So for example, here's a set of ordered pairs. 1, 2, 3, 4, and 1, 5. This is not a function. How come? You'll notice that this X value of 1 has 2 different Y values with it. That tells us that this is not a function. Now we can take a look at a graph and see if it is a function. For example, here's our linear graph. We can tell if it's a function by doing what we call the vertical line test. You may have heard this before, vertical line test. And that is simply where we draw a vertical line through the graph, and if it only crosses at a single point, then we have a function. So what would be the graph of something that is not a function? Let's take a look at this sideways parabola. If I draw a vertical line through it, you see that I cross the graph at 2 points. That tells me this is not a function. And let's tie that back into the ordered pairs. If we take a look at this point and we name it, so that's 3, 5. And if we name this point, it is 3, negative, maybe -3, approximately, okay? Notice how you have the same X values paired up with 2 different Y values. That tells us that this is not a function, okay? All right, back to linear functions, which we just wrote equations for. We graph them. Looking at the graph of any linear equation is a function. So let's write that down. Every linear equation represents a function. Now there's some logic with that, right? What's the logic attached to that? A linear equation represents a line, okay? A line can't double back on itself, so I could never cut through it and hit it twice. So that's just the logic of it. every linear equation represents a function. Okay. Who remembers function notation? So here's a linear equation, right? Function notation, we can say, instead of saying y, we can say f of x. It's the same thing, okay? So f of x is function notation. It is a replacement for the variable y, all right? Meaning the y value depends on or is a function of what you plug in for x, okay? You plug something in for x, you get something for y. So y is a function of x, all right? Function notation allows me to kind of quickly ask you to do a calculation. So I can say find f of -1. What does that mean? That means find the y value when I plug in -1 for x. So here's what I'm going to find. So 2 times -1 is -2. -2 plus 3 is 1. What does that even represent? That represents a point that would be on this line. So let's show it as a point. When x is -1, y is 1. Okay? Let's just, for the heck of it, review quickly graphing this linear equation. Remember, we can graph it from slope-intercept form. So my graphs aren't that great, but they're approximate pictures, right? So we're going to start at what? 0. Remember that 3 is our y-intercept. That's B. So we're going to graph 0, 3. And then what do? We look to the slope, the coefficient on x. So 2 over 1 tells me what? Move up 2 and right 1. So there's my line. And I did that just to see. Can I approximately say that my graph is not that great? Can I approximately say that this point is on this line? So let's just check it out. Here's -1, here's 1. So I'm close, right? Okay, so I just double checked my answer here by graphing it and seeing is it on that line? Okay? Okay. Now functions don't all have to be named f. Functions can be given any designation. So we can say g of x all right, so let's look at this. This is the g function. Why? Just for the heck of it, okay? I could call it f of x, I could call it g of x. Sometimes if we have two things graphed, it helps us to know which one we're referring to. And so we designate it by a different letter, okay? So let's find g of 2. So what does that mean? That means we're going to replace x with 2, and we're going to see what we get. So here we go. -½ times 2 is -1. -1 plus 1 is 0. So that is the point 2, 0. Huh, I kind of like that point. Where is that point on a graph? That's our x-intercept, right? It's on the x-axis because this point says do what? Move right 2 and then don't move up or down. Stay on the x-axis. So what we just found was the x-intercept. okay? Here's my y-intercept, remember, 0, 1. And if you remember, it's all kind of ties together. If you remember, on this one, because we did find the x-intercept and we do see the y-intercept, we can use those 2 points even to graph this line. And again, we verify mentally, just mentally, quick check on ourselves. Look at how we graphed it. This line is falling, right? What does that tell me? In the equation, the slope is negative. So that my picture matches what my equation tells me. Okay, so when you take a test, and I ask you to graph some equations, right? You mentally check and make sure. If the equation has a negative coefficient on x in slope-intercept form, make sure your picture shows you that the line is falling, okay? If this was a positive, then I would have expected my line to do what? To be rising, okay? Okay. All right, so the next part, which is a little more abstract for us, is sometimes kind of hard to wrap your brain around. We're going to talk about domain and range of a function. You've heard those words before, I'm sure. Domain refers to what? The set of all x values. And therefore, a range must mean the set of all y values. So we can look at a graph and say, okay, what values of x are on this graph? We'll start with a linear graph. Here's where we have to sort of use our imagination. So what do we know? We know that the axes continue in both directions infinitely. We know that this graphed line continues in both directions infinitely. So what values of x are on this line? Okay, certainly from what we see, the negatives maybe out to here. We see out to -4, we see out to 5, right? There's a point on this graph where x is 4. There's a point on this graph where x is -3 right here, okay? But because it continues infinitely, if I could extend my x-axis infinitely, what happens? The line continues. And so somewhere way out here, all right, let's make a stretch here, where x is maybe 35, where the x-coordinate is 35, there is a point on this line. It's way up here where the x-coordinate is 35. We could do that in the reverse here in the negatives, right? If I pick a point way out here, say x is -20. Is there a point on this line, this graph line, where the x-coordinate is -20? There is. This line continues coming down, So right down here somewhere, the name of that point, the x-coordinate, is -20. Oh. Sorry, let me start over. -20. Okay, I'm not sure what the y-coordinate is. It's somewhere down here. It's a negative number as well. Okay, and that just points out that we can also say that with the y values, because this line continually moves up, positive y values. Because this line continually moves down, negative y values, they're all there, okay? They're all there. So for any linear equation, the domain is negative infinity to positive infinity. And so is the range. Okay. That takes a while to sink in. It's helpful to see other graphs and also try and figure out what's the domain and the range. So even though we focused on linear equations in this chapter, we're going to take a look at some nonlinear graphs just to figure out domain and range. For example, you've all graphed these before or seen them, right? Parabolas. Okay. First of all, is a parabola a function? Let's do the vertical line test. If I drew a vertical line anywhere through this, I would only cross that parabola at a single point. What if I move over here, crossing it at a single point? So yes, parabolas opening upward or opening downward are functions. Okay? All right. Let's talk about the domain and the range, because here's where things get a little, it's different depending on where the parabola is. So looking at this one, domain, again, we have to stretch our thinking here. Imagine extending the x-axis far out there. Extend, extend, extend. Here's a value of x, maybe 40. Is there a point on this parabola where the x coordinate is 40? Well, this arrow says what? Keep on going. The nature of a parabola is it opens, it's hard to draw, I'm not a very good artist, but it opens upward and outward. It gets wider as it moves up, okay? So this is getting wider as it moves up. So imagine this extending way up there. Again, I'm not a great artist, but bear with me. There is a point on this parabola where the x value is 40. And it keeps on going. And so the reverse effect on the negatives, yeah? So if we extend that x-axis out here, we imagine our parabola getting bigger, there is a point on that parabola where x is this whatever negative number. So this parabola has a domain that is infinite. The range is a little bit different, okay? Take a look down here. Remember, range is y values. So I'm down here in the negative y values. There is no picture across from these negative y values. So y is negative, I don't know what that is, 6. There's no part of my parabola where the y coordinate is negative 6, right? In fact, y values don't start moving up the y-axis. Y values don't start until I get here. What is that number? What is the y coordinate right here? 0. And then what happens as I move into the positives? They keep on going. So the range of this particular parabola goes from 0 to infinity. Now, what happens if my parabola is situated a little differently? Okay, so instead of the previous one, which started here and moved up, this one's starting here. Let's talk about the the domain. Again, the nature of a parabola is it moves outward as it moves upward. So this is moving outward, outward, outward. Outward are the x's. So the domain is still infinite, okay? But this particular parabola, the range is a little bit different from the previous one. How come? Y values, moving up the y-axis, I don't start to get points on this parabola until I get here. That is -2. And then what happens? It continues infinitely. Okay, so it goes to infinity. If you're looking at a graph and trying to figure out the domain and the range, for the range especially, I would move my pencil up the y-axis until I get to a point on my graph and see what that number is. And then is this picture continuing infinitely upward? Hey, look. Some parabolas are upside down, right? That's a parabola. It's a function. Vertical line test. It's a function. What is the domain? What is the range? The basic nature of a parabola doesn't change if it's opening upward or downward. It's still opening outward, okay? So the domain is still infinite. Now, what's the range on this one? Yeah, if I start down here where y's are negative, remember this continues? So even way down here, let's say y is -20 here. Is there a point on this parabola where the y coordinate is -20? Yes, that's here, and it's also here. And it continues downward. So this parabola continues to -infinity on the y-axis. But as I move up, what happens when I get above this? No picture, no graph. So the y values continue up to the number 3. But they don't go any higher. Okay? If you write the range, if I ask you this question, if you reverse them, that's not a big deal. Typically, when we state the domain and the range, we start with the smallest number, and the second one is the largest number. So, technically speaking, this is proper. That's my infinity there. I would take it in reverse. It doesn't matter to me. Okay? But as a multiple choice, you would see it offered looking like this. Okay? All right. So, how to figure out if a given set of ordered pairs is a function. Okay? If you cannot repeat an x with a different y value. So, you can look at the set of ordered pairs. If you see an x value that shows up twice and it has a different y value with it, not a function. If you have a graph and you draw a vertical line through it, if it hits that graph twice, not a function. For example, there are equations for graphing circles, ovals. I don't know what that is. Let's pretend it's a circle or an oval. Is this a function? No. How come? Because as I draw a vertical line through it, I hit it twice. So that is not a function. As a set of ordered pairs, what are those 2 points? 2, 3, 2, -3. Oh, so the x value shows up twice with 2 different y values, not a function. Okay? Function notation is f of x, which is just another way of saying y. Okay. Find f of 2. So, for example, if I give you a function, so here's our function, here's our linear equation, y equals negative 3x plus 7, and I ask you to find f of 2. Okay, what does that mean? Take that value, plug it in for x, and do that calculation. So we get negative 6 plus 7, which is 1. And that represents a point on this line. What's the point? The point is 2, 1. So the x coordinate is 2, and the y coordinate is what we found. Okay? All right. And that wraps it up for functions. See you later.